Yeah, yeah. Good evening, everyone. So APSDC is different online programs in the COVID panic situation also. So APSDC in collaboration with National Skill Development Corporation. So every day conducting different webinars, guest lectures with industry experts as well as academic persons. So as a part from today onwards, tomorrow, so APSDC in collaboration with LBRC, so Mr. T. Anil Raj Garu, in collaboration with Mr. T. Anil Raju, today and tomorrow we are planning to conduct session on application of deep learning for computer vision. So start this session, I'm just giving the small briefing about the AP Skill Development Corporation. So I think most of the members already know about the AP Skill Development Corporation. It is comes under Department of Skill Development and Training. So it's totally government body. So as a part, so AP Skill Development is conducting different programs for the unemployed youth students or for the KG to PG. So we are conducting different programs for the school children's Naipunya Vikasam as well as degree students. We are establishing different centers on employability skill development centers. Coming to the engineering colleges, establish different laboratories in collaboration with industries like Dassault Systems, Siemens, so many is there. So as a part of skilling improving activities, from last few days, as a part of unlocking skill campaign, every day we are conducting different webinars with industry experts as well as academic persons. So as a part, today and tomorrow conducting session on application of deep learning for computer vision. So coming to the resource person, so Mr. T. Anil Raj Garu, so 13 years of teaching and research experience and associate professor in EC department LBRC, and he's completed his master degree in signal processing specialization in IISc Bangalore. So first of all, thanks to Anil Raju Garu for coming forward voluntarily for conducting application of deep learning. Thank you, sir. Now hand over session to Anil Raj Garu. Thank you.
Good evening to all. Is my voice audible, sir?
Yes, sir. Audible, sir. Clear, sir.
Yeah, clarity.
Yes,
Clarity
sir.
is okay, sir. Yeah,
Yes, sir. Everything is fine. Sir.
yeah, good. Thank you for Mr. Murali Krishna Garu for introducing me, and I also thank for APSSDC Skill Development Center for giving me an opportunity to share my knowledge with the students and the research society. So, IT Anil Raju, Associate Professor in EC Department of Lakreddy Balreddy College of Engineering. My specialization is in signal processing, and I am masters from IISc Bangalore. So, my today's session is about deep learning for computer vision. So, before going to discuss, let me share my PPTs. Yeah. Yes. So, is my screen visible, sir?
Visible, sir.
Yeah. So, my
Okay, sir.
topic of webinar is applications of deep learning for computer vision. So, here, if you see this title, we can see two big areas. One is deep learning, and another one is computer vision. So, coming to today's session, I want to discuss on these topics. So, introduction to digital image processing, fundamental steps of image processing, and introduction to computer vision algorithms in feature extraction, scale invariant feature transform, one of the special transform for feature extraction, and last I want to spend some time on application of SIFT in panoramic stitching for images, right? Panoramic image stitching of various images. So before going to discuss about today's session, let me talk something about the topic. Why I selected this deep learning for computer vision and its application is Now we see a lot of advancements happening in research area and in technology. Basically, advancements happening because of computers, right? So if we by any means to think a computer like a human, then all the uh, technology is coming to in a greater end, right? So in that perspective, computer vision is one of the good research area, and which will be useful for technology. And recently, it was converging into deep learning. Why? Because so many uh, things which we can feel difficult in computer vision that are simple when we deal with deep learning. So that's why I want to uh, discuss about computer vision in perspective of deep learning, right? So today's session is this one, and I planned like this. And tomorrow I am going to discuss about basics of neural networks, introduction to deep learning computation for computer vision, and convolution neural network, right? So altogether I am going to talk about the three areas. One, the basics for this topic of webinar is image processing. I want to discuss some basics or introduction to digital image processing. Then I will talk about computer vision. What is a vision? What is how can a human can understand a particular scene, and how we make, or the engineers make, the computer to see the things and understand and do the certain task, right? So these are the topics I want to discuss. So let me start my discussion uh, with image processing, right? Digital image processing. So we all know that image is a two-dimensional function, and it is denoted by f of xy. So why we call this is a two-dimensional function means here every point in an image is decided or ruled by two coordinates called x and y. They are called spatial coordinates. If you take any plane, a plane in a plane, if you want to uh, uh, identify any point, that point will be controlled, or that point will be assessed by two coordinates. Those are called spatial coordinates. Why I call it as spatial means, because I am taking those coordinates on a plane. That's why it's in a spatial coordinates. Yes, these spatial coordinates will take certain function value, which is known as intensity, right? So here I told the two things. One is about the spatial coordinates, and these spatial coordinates will take a function value, so called intensity. So if you understand clearly about these two things, then lot of things in coming slides or in this course are very simple, right? So let me give once again a definition of image. Digital image is a two-dimensional function where x and y are called spatial coordinates, and these spatial coordinates will be having a function value called intensity, right? So where if these x and y on a plane are and amplitude or intensity are finite values, then we call them as in a digital image, right? So if we want to understand the difference between digital image and analog image, in earlier days we have a photograph, right? We go to a photo studio and they take our photo and do some process with chemical and give a photograph, right? That's called an analog image. But recent technologies, in past 20 or 15 years, we are having digital cameras, right? What these digital cameras will do, so the images are recorded in a form of digital values. The process here is when light falls on the sensor, the camera, that values are converted into intensity values are converted into some real numbers or some finite values, and those finite values will be considered as a digital image, right? So this is the main definition of a digital image. That means digital image. In digital image, each element is called an epic, right? So pixel is that element in a image, digital image, and also we can represent image as a matrix. So why it is a matrix? Because image is a two-dimensional function. In linear algebra, also we consider the matrix as in a two-dimensional function, where two dimensions can be ruled by rows and columns in matrices, right? So if you understand properly about matrix operation, then it will be able to understand image, because both are two-dimensional function. In both the cases, we deal with finite values. So most of the image processing applications will be dealt based upon the matrix operations. Yeah, so here some images are given. I've taken an image of Lena. So she is a Lena. Her image was very popular in digital image processing research area, because image is considered or developed considering all the information related to image processing. That means the intensity grayscale values, the size, and all these things. So her image is very popular in processing digital image. So that's why I consider her image, right? So that image, it is having a certain size, right? So we have this image is of 256 by 256, right? That is the image size. What is this 256 56? That means we have 256 by 256 by 256 means 250 rows and 250 columns. If you want to represent that image in a matrix form, that representation will be looking like this in the second image. So f of xy is a matrix where each element in the matrix is f of 0 comma 0, f of 0 comma 1, so on up to f of 0 comma n minus 1, where n is a last, n minus 1 is the last element, right? That means we have here n rows, right? N rows, and to the next row, it is of f of 1 comma 0. Like that, we have f of 1 comma n minus 1. If you see that it is an image of it is a matrix of size m cross n. Yes, it's a image size of m cross n, where m is number of rows and n is number of columns. Yeah, so if we want to understand what is a pixel, pixel is nothing but a element in a image. So if you consider f of 0 0, it takes some value called intensity value, and that intensity value will be depending upon the light falling on a camera. So we call that one as a grayscale intensity, right? That is what about the image. And to make you understand, here I have given some shades. So why I have given these shades is because to understand what is intensity. Intensity basically is like in a light. So whether no light is there, that is called 0, and if full light falling is, it is called an a 1. That is white, right? So if you see in the screen, I have given four. In the first stage, we can identify the grayscale differences between white and black. So as the we are passing right side, the white grayscale is shading into black. Okay, right? So altogether that tells about grayscale. Here these are all grayscale quantizations. So in the last one, you can see there is a smooth changing of white light to black, or white grayscale value to black, because in that almost all the grayscale values are considered. Right. So how to understand these grayscale values, and these things we will see coming to the next one. Yeah. So before going to discuss about that grayscale, let me explain types of images. So we have in digital image processing based upon the intensity values, right? So as I told that earlier, image is of having a grayscale values, and we call that grayscale values as in a mm, 8-bit image, because we call them as 8-bit means each and every pixel in that image will take certain value. That values will be ranging from 0 to 255. So because we are taking 0 to 255, altogether we have 256 intensity values. So 256 can be represented in 8 bits. So that's why we call that one an 8-bit image. So starting from 0 to 255, right? So that I am giving here every bit, every pixel will be represented with 8 bits. Example I have given here: if I have a value of intensity 0, that 0 pixel will be represented in terms of 8 bits. So all are 8, right? 8 zeros. If I have an intensity value in the position of a pixel, in the value of a pixel, if it is 1, then the 0, all zeros in the last one I have 1. So if I have a pixel value of 127, I have all together first 0 and all are 1, right? So if it is 255, all the values, pixel values is 1, right? So that's why if you represent a pixel value with 8 bits, then we call that one as an 8-bit image. In general, in digital image processings, all the images are developed in 8-bit images, right? So and now they are going for advancements. They want to represent for higher level also. Sometimes they are going for 16-bit. Why it is not good go for a higher level? Because as a humans, we can differentiate only 2 dozens of black shades, right? So more than that we can't differentiate. Here if you see in this image, we can see only few differences. In the first one we can see differences of black and white. This is white, and this is somewhat gray, right, like that. So if you see here, these are all 1 to 256 255 to black grayscale values, but you can't differentiate here. So this is for 256, that means 8-bit image. So if you image with 16-bit, may the image will be having more data, but for perspection or for seeing that, it's not useful. Yeah, coming to the grayscale intensity shades, we have what is the grayscale intensity? Why I'm using this intensity is nothing but a grayscale. Yeah, grayscale means it's a shades of black and white. Or we can call, if you take a black color, when you are adding some light to that, it slowly develops, and at one time you will get white, or though, so we call this one as an shades of black and white. Yes. So coming to the color image. Oh, color image is also developed by 8 bit of each 3 color bands. right? So we all know that the basic colors are red, green, and blue. Because why we consider these three colors means with these three colors we can produce any color. Yeah, right. So that is that 8 bit of each of three colors. Yes. So coming to the pixel representation, so color image requires 24 bits. So 24 bits. That I will explain in coming slides. I want to spend more time on this, because if you understand at the level of bits representation, it will be easy to analyze the image and do some processing with better understanding. So coming to the three images, we can see here a original image, uh, a flower with full of colors, and coming to the grayscale. Though we can't see there any color, but we can see the combination of black and white grayscale colors. Grayscale, right? So coming to the last one is a special type of image, binary image, which is having more importance in segmentation. So binary image is nothing but a image where it is having only two values, right? So 0 and 1. So how to get this 0 and 1? Because if you want to convert this grayscale value to binary image, the process is by applying threshold. So we see the pixel value above 150 or whatever the threshold we take, that will be assigned to 1, and below that value is assigned to 0. Finally, when we operate some process on that grayscale image, we are going to end up with a matrix or an image with values 2, either 0 or 1, right? So based upon the threshold, we can do like we can get the zero color indicates black, and the white color one color indicates uh, white. So binary, by the name itself we can tell that we in that image only we have two intensity values, so we can tell that it's in a binary image. So this binary image is having more applications when we are doing segmentation and thresholding, right? So this is about images. We have basically we deal with grayscale images, because if you understand the processing on grayscale image, then the same thing we can apply for the color images also. What we have to do is we have to operate on three planes, which are green, red, green, and blue, right? So I want to discuss something more when I am discussing about color image processing, about this color image, right? So coming to the next one, I want to discuss in detail about that 8-bit plane. Yeah. So first, I have here one image, and another the second image is color image. So how the computer will store the values of pixels, and how that computer will recognize the image and store that image. So this is very important. So if I have a image here of Lena, which I call that one as an 8-bit image. So in that 8-bit image, I have, if I tell that it is an 8-bit image, that means I have 8 planes, right? Each plane represents one bit levels. So in the image, we can see here from bits 0 to 7. So this is the least significant bit to the most significant bit plane. So have here 8 by, so for example, I have taken 8 by 8 grid, right? So if I want to have to understand a particular color, how to understand a particular color, for example, if I have a chessboard of this 8-bit image, if I have a chessboard of the 8-bit image, how the pixels are represented? Chessboard means I have and the black and white colors. So if I assign a white color with a grayscale value 255 and black color with a value of 0, So what will be the image looking like? This image will be looking like 8 by 8 of 255 0 255 0 255 0 like that. So what about the bits position? So I can analyze the bits position also with a small analysis. So every bit in this, for example, if I take this one as in a 0 0 position, so 0 0 position starts with white color. If I consider, so if it is white color, so what will be the white color grayscale value? It's in a 255. It's a bit value. Binary value is 111. That means in each plane in this location, when you go down, all the values will be 1. So coming to the second one, if it is considered as black, as we see in the chessboard, alternate white and black will be there. That color will be assigned with 0. Why? Because we take grayscale value 0 for black. So if you see the pixel value going down in each and grid in this position will be all 0. Like that, so we can see in all the grids with the binary bits, right? So in the first bit, first 0 bit plane also we can have 1010 like that. So they are all binary values. So if you understand clearly about this at the bit level, so it will be very easy to understand so many things when we go for compression. So a lot of the things we consider here to reduce the storage, we are giving more importance to most significant plane because because of some reason. So that reason can be explained here. So this image, if I want to see in a plane wise, so if I want to see in a plane wise, 0 bit plane will be like looking like this. First plane will be looking like this, and second plane, and the third, fourth, fifth, sixth, and seventh plane. So if you see here, all these planes are having either black or white. So that means they are represented in terms of 0 and 1, right? So these are all planes. And one information here we can get. So if you if you take the least significant bits, those are all, there is some information which we can't interpret, right? So, but when we move on to the higher level of planes, we can have some information like edges and some shades. All these things are coming. So from this bit plane we can tell that the least significant bits cannot carry, bit planes cannot carry more information, but when we go for higher most significant bits, it's carry lot of information. So with this logic in computer vision, image compression, so they give more importance for higher bit planes, right? So how to arrange these things? So if I take this plane and arrange like this, so all these planes if I arrange and keep them one by one, right, on one upon one, then I will have 8 planes. So 8 planes, if you bind them, and it will be looking like an 8-bit image. So it is all happening in the computer. It will store all the data in different planes like that, right? So altogether, if you add all these planes like this, then you get this type of grayscale image. So this is about grayscale image, right? So this is very important, and if you want to understand better about better about image processing, so at this bit level if you understand, so a lot of things are very clear. So coming to the color image, as even though we deal with grayscale processing, but it is very important to understand about color image. So what is this color image? So what is the significance of this color? Because in real world, all the images are having are with the colors. So, and the color is also one of the important feature of an image. So it is better to understand. It is good to understand about color image. So color is defined like a light, and we all know from basic physics that if you want to have a color, if you are able to composite 3 colors, RGB, then we can get any color representation, right? So if you see this RGB, and RGB is again an 8-bit, and G is again 8-bit, and blue is 8-bit, right? So if you see in this figure, so all this one again a red, this one is an 8-bit, and this one is an 8-bit, and this one is an 8-bit image, right? And all together we are going to get this color composite. Okay, so from this we can understand, to represent a color image pixel we require 24 bits. Why it is 24? Because each and every pixel in color image is defined by, or it will be assigned with three 8-bit planes. So 8-bit plane means a red plane, green plane, and a blue, a red band, a green band, and blue band. Each band will be of 8-bit, right? So that to understand, to get a color image, we have to understand about 24-bit, right? So for example, if I want to get a red color, so where we can have here for about this one, so if you, the composite value is this one, so this is a white pixel, and if you see here, this one is 0, black, this green is 0, and blue is 0. Because this is white, that means we are giving more significance for red band, and we are not giving significance for green and blue band, they are 0. So the reflection of this one, we can see here a red pixel. So when we see in a pixel level and in a binary level, only red plane will be having 255, and coming to the green and blue band, they are 0 and 0, right? So like that, if you want to represent a color in a pixel in red color image, so that will be given by 24 pixels, right? So this is what about understanding of color image and grayscale image, right? So coming to the yeah, so next one, some images we can understand, very familiar very famous images. As we are going through different technologies now, image processing in medical images is going beyond that means a lot of things are happening in imaging technologies in especially in medical imaging. So with the basics of those, some images they have evolved, so called volume image. Right here, volume image, we are giving a special name in a volume image called voxel. Right, so voxel is nothing but like a pixel, but here voxel is in a not two dimension, it is in a three-dimensional piece in a image. Yeah, so if you see here some, I want to discuss about this because when we go for computer vision, so these things we deal with three-dimensional objects. In three-dimensional objects, we take in a particular piece of element in an image three-dimensional object, that is called voxel. What is a voxel? So voxel can be understood like this. In medical image processing, when the MRI scan or CT scan, they are taking, they are going to do some projections. So each projection will be giving one image. So if you see here, they are going to scan a image, MRI image. So like this, and here are all the slices. I have first slice and second slice, like that we are having 10 slices, right? So each slice is of thickness 6 mm. Okay, so these all slices are arranged like this. So here if you see, this one is in a small slice, so that's why it is small in size. As it is coming towards this one, so we are having the bigger one. So this is last one related to this image, and this first one related to this image, right? So or like that, they are going to take all the images, and based upon all those images, they are going to analyze some pathological conditions in medical images. Yes, so when we take this image, so they are going to consider the thickness of the image, right? So earlier we didn't discuss about thickness, just we discussed about only plane, but here in this volume image we can discuss, we will discuss about thickness. So that means we have length, height, and at the same time depth also there. So depth also there, right? So this is called a voxel, volumetric pixel. We name it as a volumetric pixel. So to understand in a better way, we can see here, this is in a brain image having some tumor here. So to analyze this tumor, they go for MRI scan or CT scan. So what they will do is they will take this type of projections, and each projection will be having certain depth or certain thickness. So that thickness, with that thickness, they can we can call that one as an voxel. So see here, this one was enlarged, and this is the area where we have, but this is also having some thickness, right? So this is the way a lot of image processing techniques, especially in medical imaging, they consider these brain images or any organs. If they want to go for scanning, they take these projections, slice. We call this one as a slice terminology, and every slice will be having thickness. That thickness we call some depth in a pixel. So we totally call that one as the voxel. At another area of images is called, these are all developed images, and a lot of developments are happening in these imaging technologies. Like in medical images, we have that slice terminology. In spectral images, these are also very much useful in medical images, and to get satellite images, all these things, right? So here, the if you see this, we call this one a spectral image or confocal image. So what is this confocal image means? We collect color. We have a image of a grayscale, but we can't have particular information. So to analyze or to enhance the information in that image, we append or we use this spectral type images, so that this image can be understand in a better way when we see this the same image in spectral band. Yes. So if you see here, this maybe doctors also can diagnose in a better way when compared with this grayscale image in spectral images. Yes, actually, these are not the real color we have in body organs, but for better understanding or to enhance, to get more information from the image, we are using the spectral images. So the process is here. Here there are some bands of colors are using blue, green, and some shades also there. It will be every pixel will be defined with alpha, x comma, y comma, lambda. Lambda will be defined by a band of spectrum, right? So if you add all these images, we can get this confocal image. We can call this one a confocal image. So these images are very much useful in remote sensing. When you when we want to get images of far distance, like Hubble telescope, like telescope images, we can't see that objects with with far images. With they just lay in a position of light, but based upon some processing through spectral images, we can append some colors and we can better understand those images. Yeah, these are the special images we are having in image processing, and these based upon this, computer vision and deep learning techniques are giving more importance for these spectral images. Yes, coming to the another point, which is basics of image processing. So when we want to understand image, or if we want to enhance the image, so we want to understand about two things called we want to understand about a concept called resolution. So what is this resolution? So in recent days, we are going to have a lot of technologies having emerging in mobile phones also. So the main parameter that will rule the camera, that mobiles are cameras, right? So now, so all the people are interested to have a good good technological values uh, equipped in that cell phone. And one parameter is camera. So if you go to buy a camera, they will. If you go to buy a mobile phone, the mobile phone price will be differentiated based upon the main parameter called camera, and they will tell like that. Then they will tell like this. So this mobile is cost of 10,000, and another the mobile they will show it's a cost of 20,000, and they will tell that this camera is having high resolution. So what is that resolution? Why? How this resolution will help us to understand or understand about image or to do some image processing for better understanding? So I have given here. We have two images, two images, a pair of images. For example, I want to talk about spatial resolution. What is resolution means? We can explain that in two ways. One is about spatial resolution. So if I have an image, if that image is considered with only 10 pixels per inch, right? So that means a 10 by 10. So if you see here, this matrix size is 10 by 10, and I want to represent in this matrix a letter A. And if you see the second image, I am representing with 20 pixels per inch. So this is a 20 by 20 grid. And if you go beyond here, it is in a 100 ppi, that means pixel per inch. So which where we can see the image clarity. So we can see the image clarity here. Why the image is so clarity good? Because the number of pixels I used in per inch is more when compared with this one. So here we can have a shape, but it is not clear. So, but here I can have a very good spatial resolution. We call that one as spatial resolution. So from this we can tell that spatial resolution is nothing but a small reasonable lines or pixels in a unit area. So if the spatial resolution is more, means the number of pixels per inch is more. Spatial resolution less means number of pixels less. So this is what they are doing. So when we go for to buy a mobile phone, they will tell that it is in a 20 megapixel camera we are having, or 8 megapixel, like that. So if the pixels number of pixels are more, then the image clarity is more. So one more example I have given here. It is there, a high resolution and low resolution. So high resolution, if you see this image, it is looking good when we compare with low resolution image. So what is the difference between these two images? Here the number of pixels per inch are more, and the number of pixels for a particular inch is less. That's why we have this type of checks effect, which is called checkerboard effect. So when we are not having proper spatial resolution, we call that one as a checkerboard effect. That means the image is not having good clarity. We have a small checks like things, then we call that one a checkerboard effect. So when we go for grayscale resolution, we have here some bits. So see here, we have taken only 4 grayscale values to represent a particular image, right? So 0, one grayscale value, another and another. When we go here, 5 bits means 2 power 5. 2 power 5. This means 2 power 4 means 2 power 4 means 00011000, like that, right? So only 4 colors they have considered, but here we have considered 2 power 5, more number of quantizations here, right? So what is the effect of this grayscale? So this is also important, right? So if I have a image of like this image, when we compare with these two images are giving more grayscale resolution. What is this grayscale resolution? Here in this image, all the grayscale values are considered. But when compare these two images, here we can have this type of some shade which is not real, but because of less grayscale resolution, we are getting this type of shades, which is called false contour, which is called false contour. This is called false contour effect. Why we get this false contour effect? Because we are not using all the grayscale values which are used for an image. And finally, we have here in a binary image only two shades. We have white and black. Almost it gives some information, but lot of it gives some data, but lot of things are features are missing here, right? So this is what about grayscale resolution. So these two are very important. Why? Because image is defined basically by two parameters. One is spatial coordinates x and y, and another one is grayscale intensity value. If more number of pixels are there, then the representation is good, and we can have very good spatial resolution. When you go the same way for grayscale, so altogether for an 8-bit image, we can have 0 to 255 grayscale values. So if you use all the 256 values, then the image clarity is good. At least we have to use 2 power 6. Less than that, if you are using grayscale values, that means only 32 or only 16 grayscale values. If you are using, there will be effect in the image. That effect is called false contour, right? So to do analysis, we should take care about these things, and these are all very useful. We do some analysis with compression, segmentation, and color image processing. Next, so coming to the fundamentals of image processing, uh, we have altogether 10 fundamental steps. So they are image acquisition, enhancement, restoration, color processing, wavelets and multi-resolution processing, compression, morphological image processing, segmentation, description, representation, description, and object recognition. All these steps are classified into two groups based upon the operations or processing. So if you consider first 1 to 7, they are all processing image processing techniques, where we get where we give an input as image and output as an image, right? So what is this input as image and output as image? That means these are all very simple image processing techniques. If I have some problem in the image, for example, the intensity or contrast is not there, simply I will improve that contrast and I will give the output. But the other last three things are, these are the things where we need some knowledge beyond the simple applications, like describing the information in the image, or representing something in the image, or recognizing some information. For this, we can tell that so we require some attributes to get the output. So here these three are some special cases where the image outputs are attributes or not regularly images. And uh, when we want to see the most of the applications, we go for representation, object recognition, description, segmentation. They are all based on computer vision. Why? Because they required some description, and they required some more knowledge when we compare with another steps, right? So let me discuss or classify these two things, and I I will discuss about these steps, like image acquisition and enhancement. Yeah. So coming to image acquisition, how we can acquire an image is very important thing. So first thing we required here, this light source is very essential. When light source falls on a scene or the element what we want to get picture, so that will be for reflected onto an imaging system. And in the imaging system we have sensors 2 by 2 array sensors, and that sensors, the light will be reflected based upon the reflection of light. So if no light is reflected, then that is 0. If maximum light is reflected, then that is 1. So depending upon the intensity values of that image, so this image is we will get. So we call this one as an imaging plane. Once if you collect that information on imaging plane based upon the sensors values, they are going to be digitalized. Finally we are going to get a digital image. So altogether the process we have in camera is this process. So we have a scene what to what want to make a photo. So when light falls on that, mean in that this, if you think this one is a camera. In this camera we have a sensor plane which is called image plane. The light falls on the object, and the reflections will fall on the sensor plane, and that sensor plane, based upon the values, it is going to digitalize, and finally we are going to have this information on imaging plane. Okay, so this is what we are going to see. So to understand about image acquisition, so for better image processing, two things are very important. The light is very important. That's why if the light is not proper when we are getting a photograph, then the information we are getting on image plane is not clear. Right, so light is very important. At the same time, the sensors what we are using are also very important. Right. So coming to the enhancement, second one is enhancement. Enhancement is in a simple technique. So we have some image which is not good to see. We can tell the contrast here is not good. So to develop that contrast or to improve that contrast, we do some processing called image enhancement in spatial domain, and we will get an image which is a good contrast image, or equally balanced contrast. So this is what the two, we can see the difference here. These two we can identify. So this one is an enhanced image, right? So I have given here a spatial domain, means here all the pixel values I am taking, and in on each pixel we are doing some processing based upon the technique what we are using, and we are going to get output as an enhanced image. And another one is there called image enhancement in frequency domain. So sometimes the image is corrupted with certain noise called spectral noise. So if you see this image, so this is an image which is having some noise in terms of pattern. So see here, some pattern is there and it is not looking good. So what type of process we have to do and to get in a better image? These type of images we can go for enhancement in frequency domain. So if I have any type of this spectrum, this pattern is having with an image, then I can go for image enhancement in frequency domain. So we consider this pattern as a periodic noise. So how to remove this noise? We have to go for a small procedure. First, I have to convert this image into frequency domain. So by using Fourier transform, two-dimensional Fourier transform. So this is what the two-dimensional Fourier transform of this image. Right. So if you clearly see here, some pattern is there here. So dot. So this one, this dot, this dot, this dot. These are all the dots. So these are all dots which are creating problem in this image. So they are all placed in a periodic way. So that's why we call this one as a periodic noise. So ultimately, to get a clear image, what I have to do? So if I, by any means, if I remove these dots, or if I filter out these dots, then I will get a clear image. So that's what they are doing in frequency domain. So here, if I have a special type of filter called band stop filter, so band stop filter, and if I apply filter on this frequency domain image, then this band, see here, this exactly fit here, and this the frequencies on this one are eliminated. So why? Because we are considering here band stop filter. So these bands are stopped. So only other things are allowed, right? So if you apply this band pass filter on this frequency domain, we will get a band filtered frequency domain image, and that image, that filtered image should be reconstructed back into spatial domain by applying inverse discrete Fourier transform. Then we are going to get this image. See here, so it is in a very clear image, almost enhanced image. So when we compare this image with this image, there is no comparison in terms of noise. So almost all the noise is cleared. So this, as we are doing enhancement, removing the noise which is there in frequency domain, we call this one as image enhancement in frequency domain. So coming to the image restoration. So restoration is also a process of enhancing or improving the quality of image. But here the process we do here is not in a regular way as we do in image enhancement. But here we apply some objective analysis, and we do some noise elimination techniques. So what is restoration? So before going to discuss about this enhance improvement, what is restoration? Restore means to build again or to reconstruct back, right? So so if I have a photograph which is of old photograph, which was corrupted with uh, some some chemicals or foil on that image, and but that image is very important and there is no other copy. In olden days, only digital, they don't have any copies preserved, only have analog, they have to preserve those copies only, right? So what to do? So to get back that image, now what to do is, we have some good techniques called image restoration techniques. So by using image restoration techniques, so we can get a clear image like this. So here we restored the corrupted image and get back the color enhanced image or improved image. So this was named like image restoration. So some techniques are there here to restore the image. First, in this process, we have to understand what type of degradation that image is having and how to apply that restoration. So it's important, right? So this is about restoration. So I'm not going in detail about these things, just I want to make you to know what is the terminology that we use in image processing. So if you understand this terminology, it will be easy to understand computer vision and deep learning. Right. So coming to the other fundamental steps called color image processing. Right. Color image processing. We have two types called pseudo color image processing and full color image processing. What is meant by pseudo color image processing? Actually, in this processing, the grayscale images are there, but those grayscale images are represented by appending color, so to extract more information or for getting a good look like that, right? So the process we have here is all the available image grayscale intensity values are represented like this. So all the grayscale values are represented on 0 to 255, and they will use a slicing plane. So that means above the plane intensity values are assigned with some color, and below the plane slicing plane, they are assigned with another color, right? So I have taken only these two colors in this representation, but when we come to this image, so this is a knee MRI, a grayscale MRI of a knee. So here the ligaments and there's some bones. So to analyze this image to a doctor, it will be very difficult. But when we do some processing on this image and make this image with color appending, so then doctor can give better analysis. So if you see here, a lot of things are there. Most of the cases, the knee problem will be having this ligament. So if the ligament is not available, then they treat like they go for higher medication, right? So to understand what is the gap between these two, and it will be difficult here, but here we can have good analysis. So this is a pseudo color MRI of a knee created with three different grayscale scans. So here they have used three different grayscale scans, right? So what is pseudo color means? It's another name is also there called false color image processing. What is meant by false color image processing? It is not true, just we are appending those colors. And recently in film industry, a lot of experiments are going. They have taken old films and they want to remake those films with color. And earlier days they have uh, black and white image we call, they are all gray in color. So they are doing this false color image processing, and they are giving the output called color image, right? So some few films like Maya Bajar and some films, they have done some experiment and they have succeeded. If you see that film what was processed with this pseudo color image processing, almost we can have a color effect, but we can identify that they are not real colors. They are false colors which are appended in on the grayscales, right? So that is what the information. And here one more image, the moon image. So to understand the valleys and the mountains are different shades on the moon with different colors. This was an image created by NASA for some purpose. So it give more information when compared with this one. So this is about pseudo color image processing. So coming to the full color image processing, the name itself will tells that we are considering here all the three planes. So our plane, green plane and a blue plane, if you do process on the 3 pixels and get the output, then we call that one in a full color image processing. So earlier one, we are going to have only one grayscale image. We are just appending colors there. But here in full color image processing, we are taking 3 planes pixels, and we operate our operations or processing to do get bet output. So that we call that one as a full color image processing. So what we see in full color image processing, so if the color of the image is not good, so or we can call the tone correction. We can tell that this is in a tone correction. So tone is a feature of one parameter we discuss in terms of color. So to enhance this one, we have tone correction. So see here on all the planes, they have enhanced like this. This is a transfer function. We have all the intensity values are somewhat enhanced, right? So that's why in all the planes they have taken like this, right? So they have given less importance for these things and high importance for this thing. So it is not a smooth curve, it is an SS curve, sigmoid curve. We can call this one as sigmoid, a smooth sigmoid. That means this gives information. So here the most of the values are giving high. That means we are giving high resolution. High intensities. And for small values, for these values, we are giving less. So that means high colors will have high, low colors will have dark. So that we can have a good contrast, or we can have a correct color information. Here also the same thing. So see here overlight. So high contrast we can tell. So to decrease that one, what we are doing, we are having a this type of curve. So what is this? This tells that the values are taken down. So taken down, right? So that's why we decreases the light intensity. Then we can have this type of color corrected, right? So one more thing here you have is about uh, information about another image where we can control the intensity. Here the information and the color in the one is almost all dark. So to get a better information, so we can have this type of correction. The values are improved like this. So values are improved like this, and these are all operated on. We have to think keep in mind is that we are doing on every plane. So that's why I told, if you understand clearly about grayscale information processing, so it's nothing but, if you are going for color image processing, the same thing we are applying for three planes and we are getting the output. So here also the intensity is dull here, very low contrast. They improved the contrast by taking exactly this one is like this and this one is like this. Okay, so this is about correction. We call this one as a tone correction. And one more important point is called histogram, color histogram, color histogram. Here, one example they have given, color histogram is also full color image processing, but here we have HSI. HSI is another representation of color. H means hue, S means saturation, and I means intensity. So this is also color representation in another way, HSV. Altogether, we have different models in color image processing. RGB model, next CMYK model, cyan, magenta, and yellow and black model, and HSI model. HSI model will be useful for analysis of images for research purpose. So here we have this one, and see here, if the image, if you clearly see, observe, the chemicals and the information on the table were not clear in the first image. This is the original image. To do some process and get better information, we are doing this histogram equalization. What they have done, so we have three parameters here. H means hue. They are not in giving any doing any information changing here. Just they are actually taking whatever the old thing has here, but here the saturations, they have some improved. See, not, it is not starting from zero, it is starting with some minimum value. So this information we will have to improve the saturation, we are going to get that one. And this one histogram, if you plot a histogram like this, and this histogram, we see this is not equally distributed, and here these are values high and these values are low. If you make some process and do equally distributed, that means you are giving importance for all grayscale information, or all intensity information. So in a image, then it gives good information. So we have one topic in enhancement called histogram. Histogram is nothing but, it's a graphical representation of pixel occurrences, grayscale occurrences. So uniform histogram, normal uniform histogram, or equal histogram, and histogram matching, some methods are there. Here it is a method which is used to enhance the color image, where the histogram of the intensity is considered, and it makes in terms of medium 0.5 is improved. So we to make the distribution distributed to all the pixels, right? So this is about full color image processing. And coming to the other thing is called image compression. Image compression. So compression, all if when we think at the student level, we think like this. Compression means we are making the image cut, or going to resize. But we have to be understood that uh, image compression is not resizing the image size, but we are concentrating the storage size of the memory storage. So that is the difference we have to understand. Image compression, we are not doing any resize of the image, we are making the size of the storage reduced, right? For example, if I have a image of uh, 8-bit image of 10 pixels, 10 by 10, that means 10 by 10, 100 pixels into 8, 800, 800 bits required, right? 800, each pixel will be of 8 bits, so 800 is required. By any means, if I am making that 800 bits to 400 by using some image processing or image compression techniques, then I call that one as an image compression. Now simply by making 10 by 10 into by 5, it is not image compression, right? So here I have we can see some information. Here it is this one is 100, that means 50k, 53 kilobytes images are there, bytes are there, so full clarity image. And it is 25k, that means 80% of this one is considered. And here only 60%, 60, 40, and 20, and 10, and 0, that means 0.65, 64, so very reduced. So see, we can compression, almost the quality of the information is missing here. So up to this some extent, so we are getting the same information, even though we can't pursue that information loss, but here we can see that information loss. Yeah, so some information is missing here when we are doing compression. So compression ratio is very important. Compression ratio is nothing but actual number of pixels, n1 by n2. So where we have to see the ratio, so how many given pixels are there and how much compression we have given. Based upon that, we can decide compression ratio. So from this image we can understand, as we are going with a less compression, almost we lost information. And some techniques are there called lossy compression and lossless compression. Lossy compression means we lose some information by reducing the data, like JPEG is a lossy compression. And lossless compressions are there, where the coding techniques we change and we see that the information is not missing, right? So it is about image compression. And another things are there called morphological image processing. So where morphological image processing is also important, we want to extract some information from the image. In this image we have some processes called dilation and erosion. Dilation and erosion, and some other techniques are there called morphological grade scintillation. Please remember that I am just giving information, basic information about image processing. I am not going in detail or explaining about the functionality. So because if you understand this terminology in about image processing, it will be easy to understand computer vision and deep learning. So here I have taken dilation. So that means if you see, this is the image. This original image is bolded. We can call this one bolded. So by some dilation operations we have, the thickness of the image is improved. Erosion means subtraction. Dilation means added. We can tell like that. Erosion means the thickness of the original image is reduced, right? Some other informations are there. Internal boundary, we can enhance internal boundary also. We can eliminate internal boundary is removed. So see, this the internal boundary is removed. And external boundary, so external boundary, so they have concentrated only on external boundary. And internal boundary, almost it is in black in color. Yeah, this one is morphological. Gradient means separation. Some gradient operations are there. And thinning is original one is the size of the that letter is made thin. And thicken means it was somewhat improved. And skeletoning. So these are all the techniques we have in morphological image processing. Morphological image processing deals with shapes. And this is also important to understand the object shape of the object, right? And one thing is there called multi-resolution. This multi-resolution means, as we move to different resolutions, we can get information at different levels. So here it is called an image pyramid. This is high resolution, and this, as we are moving to a lower resolution. So resolution means we are decreasing the number of pixel size here, pixel size. So this is what the analysis. And multi-resolution analysis we have with wavelets. We do with wavelet analysis. In wavelet analysis, we take a image, and we do multi-resolution analysis. Means low frequency and high frequency, and vertical and horizontal. The image is divided into those four wavelet coefficients. Low frequency, in high frequency we have three. They are vertical, horizontal, and diagonal. So based upon this information at different level resolution, we can do analysis. And we have image segmentation. So here, see, this outer line is segmented. The outer line is segmented. In image segmentation, we different techniques. We are going to discuss in detail about those things when we are discussing about computer vision. So segmentation starts with description. So we can describe some things here. So this is very important important concept for image computer vision. So to do any analysis of a image, first we have to identify what type of object it is. So to identify that object, we have to use image segmentation. Based upon the segmented image shape, we can analyze what type of object it is. Right. So these are the examples I have. We have for this image processing. So let me go for computer information. So up to this, let me conclude with image processing. Image is a basic thing important for computer vision learning, and whatever things we do with computer, when we go for computer vision or a lot of analysis, they are all doing now based upon the analysis on the image. For example, marketing, telemarketing, and medical operations in surgicals, they are doing using robotics. For all those things, what is the basic thing? They take the image and they do some processing, like low level processing, medium level processing, and high level processing based upon the application, and they get the work to be done. That means image is very important, right? So we have different techniques as discussed here. So out of these techniques, they classified into low level image processing and high level image processing. Low level image processing means simply, if I have a image, I do some operations on that image and I will get enhanced image, and I will restore the information in that image. But high level image processing, where it is important to understand the analysis of the image, to understand some information what is there in that image. So that part we can do with simple image processing techniques. So we have to go for computer vision, right? So let's move on to computer vision. Before going yeah so Before going to computer vision, uh, 1 second, let me have water. Thank you. Yes, now let's move to our topic called computer vision. Before going to understand about computer vision, so let us think what is vision. So this is a very simple to talk about, but when we see the process that is happening in vision, is very difficult to understand. right? Human vision performs multiple visual tasks quite effortlessly and effectively. So many times we are thinking that we are not capable of certain things. But when we see the mechanism of human eye that God created, uh, we can't understand how much tasks we are doing without any effort within a human eye, right? So I want to tell that a lot of mechanism is there in human vision, right? So let us see what is that. How is visual information processed and understood in biological system? Right. So let us, before going in detail about the technology of computer vision, let us see how humans can understand a particular scene or a particular particular information when we are visualizing. For example, if I have image or a scene here, one person is throwing a ball, and one person, a boy, is catching that ball. What is the process happening here? So this is what visual information or in human vision, visual information processing. Can I can think about this process? So one person is throwing a ball, and this boy is catching that ball, right? So how to understand this? So let me move to this one. The steps involved in visual information processed or processing, right? So the light ray of the ball passes through the eye and strikes on their respective retina, right? So first, to understand the object, or to see what object is coming towards, first that object light should fall on, passes through the eye and strikes onto the retina. So this is one first step. Then retina do some preliminary processing before sending the visual uh, response through the optic nerves to the brain. So that means it will adjust its lens and see how much far it is and how much time it reaches to a particular point, and this will be all preliminarily processed, and clarity and adjustment all will be done by the lenses that will be available, and it that will be processed to the brain. The brain taps into its knowledge base, classifies the object and dimensions, and having predicted its path, decided to act on it by sending signal to move the hand and catch the ball. So these are all small things are happening in our brain. First, the light should fall on the ball, and that light should reflect on into the eye, and that should fall on retina, and that retina should tap that basic information, what type of object it is, what is the dimension, what path it is coming, uh, and it should decide and to send the signals to the hand to catch that ball, right? So unknowingly, these are things that are happening every time when we are doing when we are seeing, right? So it is very mysterious to understand. These are all things happening in a fraction of seconds, tiny fraction of seconds, almost no conscious effort, and almost never fail, depending upon how much prior catching practice we have, right? So almost mm, uh, we can identify the object, and we can see what to be necessarily to be done, right? So to catch that ball, this much is happening unknowingly inside our process of understanding so information through visual, right? So now as we are calling computer vision, so computer vision, so this is what the god given model, What is God given model? If a object is and through eye we can identify that, and the information is sent to the brain, and brain reacts and it will send to the parts of the body and catches. So this is what natural model. So we have to make this model. We have to make this model, or we have to get a artificial model, which what are all active actually this eye is doing. So if we are able, if we are able to produce an artificial model, or a vision, artificial vision through computer, then it is called a computer vision, right? So let us see what is computer vision. Recreating human vision is not just it isn't just a hard problem. It's a set of them, each of which relies on others. So there are a lot of links to create a human vision. Or in human vision, we see that first the retina is receiving the image, and it will be processing, and it will be bringing to the brain, right? So uh, this is it's not a single thing. It's in a say set of problem, set of things are happening. So what we have to understand, how we can understand. So can we make a model, artificial model? So that's what the introduction to the computer vision is happening. So the objective of computer vision is to make computers see and interpret the world like humans, and possibly even betterness, right? So that's what the main objective of computer vision. Computer vision, in one word we can tell that, so to interpret the world uh, by the computer, right? So by the computer. More formal, computer vision is concerned with feature extraction, analysis, and understanding of useful information from single image or a sequence of images, right? So this is the task. So here we have two models. This is a natural model, given model. So eye is getting information, and it is sending to visual cortex, and again it is getting information to some information mm, center, thalamus, and then again it is sending that information to different parts. So here we can see one robot humanoid, you can call an humanoid. uh, the It is also seeing that here we have certain equipment which will see the world, or we can call a camera, and that camera information is every time passing through the processing center, and here it will be processed and make that information processed, and to understand what type of object it is. So we are making a computer to see and process that image by using some techniques, and make the information to understand. So that's why we call this one as a computer vision. And they are very important. They are very important in so many applications. And so like designing robots, whatever the way we can, we have so many sensory organs. Out of all sensory organs, the effective sensory organ is vision. So if you are making a model, and give that model to an artificial system, it will make us to understand a lot of things in a better way, right? So it involves the development of models and algorithms to achieve automatic visual understanding system. The main aim of computer vision is to design a models algorithms to achieve automatic visualization system. So in this involvement, is the process, the main things we are going coming are features extraction and analysis, right? So there also, when we see in a process there, the ball is coming, so we have to identify the features of that that object. So the the ball means it is round. How can we tell that is a ball? That is a round. It is a feature. Yes, it is having certain color. It is having shape. It is color. It is having size. So based upon all those features, we can understand a particular object, right? So in computer vision, one of the main thing is feature understanding and analyzing is very important. Let us move to understand about features. So features is a piece of information about the content of an, right? If I want to understand an image and do some analysis, first I want to understand what are the features that are available in that image. Features may be points, features may be edges, or features may be objects, right? So if I gave an image, if I ask some person to identify what are the objects that are there, then he can tell some information based upon the size. He can tell that this is the object available. So we have to teach these things to a computer and an algorithm to extract that information automatically. So in some applications, it is not sufficient to extract only one feature to obtain then relevant information from the image data. So in those cases, have to go for more number of features called feature descriptors, and all them are stored in a feature vector. This is a common information. Sometimes when we want to get an information about particular animal, uh, uh, a horse and a mule. So only shape is not necessary there. So we have to go for different more number of information. Here also, to get better information about features, we are considering more number of features, right? So that's what feature extraction. And we will make a feature vector where that vector contains a lot of information related to features. And the feature extraction techniques are edge detection, corner detection, and scale invariant feature transform. So from this slide, I want to tell that edge is one information which is a feature. So if I want to recognize a face of any person, I will see the face of the person based upon the shape or edges, right? Whether the face is round or oval in shape or any shape, based upon that classification, give that feature, it gives more information, right? So like corner detection, somewhere corner detection important, and some special features are there which are invariant features, which are scale invariant features that we will discuss in coming slides, right? So this is what important, if you are able to understand features very well, and if you create a feature vector, then it will be very simple to do the computer vision processing in a simple way. So this is one example we consider here. I want to understand a classification problem about vehicles. So in that vehicles, I want to concentrate about the bikes, right? So for that, what I have to do, I have a bike here, and this bike is having a features, and let me come to the feature box next, and let us see these are the features. So what are the features we can extract from this bike? It is having a wheel, and it is having a handle, and it is having a portion, and some other are there. This is a speedometer and the wheel axis, like this, right? So these are all the features. So if I want to design a system, a classification system, where that classification system should automatically classify the motorbike, If if some number of images are given to that system, it should classify out of them what are motorbikes. So in that cases, how it should act, or how this will information will help you to understand about computer vision. Right, the main task of the computer vision or objective is to design a model how a human can understand the information. So in the same way, we have to design a model. Here basically humans also understand the information based upon the features. So based upon the color, based upon the shape, based upon the texture, and based upon the what we call size, all these are the features. Here also we are taking the same thing, feature extraction algorithm, but in the place of human, we are designing some certain algorithm. So this algorithm will make understand the information in terms of features, right? As I told, it will be better to get a feature vector. So if I want to get a better feature vector about bikes, I will take more number of bikes, and more number of bikes will have I will convert them into feature extraction, and I will design a feature vector here. If I have feature vector, where this feature vector is collected information from more number, here 10,000 images are considered. From all those 10,000 images, we get some information in terms of features, like what will be the size, and what will be the wheel, and how the wheel forks will be there. All those information is stored in feature vector. If this feature vector I am having, and the classification will be simple based upon the classification algorithm. If any new image is given, so this feature vector will be compared or matched with that new image features, and if that particular threshold is more, then we can decide that that image given is in a, otherwise it is not, right? So this is all basically a feature extraction problem, right? Feature extraction plays a role in computer vision, and uh, those features we can see as edge detection. So let us see about edge detection. The basic feature that can extract automatically from an image without any shape information is edge, right? Without any shape is just we can extract information like edges. So it is called edge detection, and it is very important. The basic operation of computer vision is detecting the object based upon the edges. If I keep a apple on a table, and if I take a image one, uh, if I process that one, if first processing I will do is edge detection. So I will take that image and process that image. I can identify that some object is there which is round in shape. So based upon that, I can get some image information, right? So that means edge detection is very important here. So here some edge detection operators are there, second order, first order operations. So this is the original image. So we have a Laplacian operator, Cannet operator, and this is Sobel operator. Sobel operator, where Sobel operator, this is x direction, and this is this is vertical direction, and this is horizontal direction, right? So operator, these are all basically masks. Some mask will be there, to minus one, minus minus one, minus two, minus one, 0, 0, 0, 1, 2, 1. So these are gradient operators. Those masks will be converted, or we will on this image based on the operation, we are going to get the edges. So here this is a Laplacian operator edge detector, and a Cannet edge detector, and Sobel. We can see here two types, this direction and this direction. If both are added, we got this one. So when we compare with this image, this one, we have this edge information. From this, we can tell how many circles are there, how many rectangles are there, how many vertical bars are there, and how many horizontal bars are there. So this will give some information, right? So coming to the next one is about Harris corner detection. So this is also one feature we have, corners. To identify the edges or to identify the objects, the corners are very important. So finding the differences in intensities for a displacement in all directions. So we have a small formula here. We will consider a small window, and we shift that window. Shifting window, we will what are the intensity changes. So if any intensity changes are there, then I can identify that there is some edge. So from that edge, we can identify the corners. So one of the best corner detection here is corner detection. So if the image is given, these are the corners we have. Corners we have. Corner detection is a very one of the important feature in extracting the feature and at the same time recognizing the object, right? So coming to the need of scale invariant feature, right? So our task is my task is to go in detail about scale invariant feature transform. Why? Because this is one of the best robust transform robust feature extraction technique in computer vision. So the name itself is called scale invariant feature transform. Scale invariant feature transform means it is a feature extraction technique where you can extract the information even though the given information is not exactly the original image. That given information may be having the information related to original image but not in same size, shape or alignment. In those cases we use this scale invariant feature transform. Let me explain the need first, right? So if you take this one as in a corner, this is a corner. If this is the original image, if this is the output image they have given, there is no comparison between this image and this image, because in this image the size is small and in this image the size is big, but both are same curves, both are same curves. But when we see in terms of images, both are different, right? So what we can get here, the same image is scaled. Sometimes we also face the same problem. When we see the aeroplane on land, it is big. When we see the same aeroplane flying, it will be very small. But same object, what is the difference there is just a scaling problem. So in these cases, if I have a corner edge detector with say a small window, it will not work. So in these cases, we are going for a scale invariant feature transform. What is the scale invariant transform? What is the need? It is obvious because corner remains corners in rotating images also. So we see that corners, even we rotate, but the corners will not be changed. But what about the scaling? Scaling is a different factor. If you zoom, the image size will be more and the features will be distracted. So entirely it will tell they are two different images. But what is our goal? How to see those two images with a feature extraction technique. Both are same, just they are scaled. So that information we have to. So a corner may not be a corner for that image as like this. So here this is a corner, but it is not a corner here. For example, check a simple image below like this. If you use a small window, this is telling that this is a corner point, but here it is not a point. So in these cases, the corner detector fails, a hairy corner or this feature may fails. But this is a very regular problem we face, scaling. How to deal this problem? So this problem can be by efficient feature extraction transform called scale invariant feature transform. Let me give an example. Here I have a small toy. A small toy is there in this image, and same information, but another image is there. Same toy is available, but in different alignment, in different orientation, right? So our goal is, if I ask a human or any regular human visualize system, I show this two images and ask a question, is this image related to this image? Human can simply tell that the image is related exactly the image, but it is a small in size, and the orientation is somewhat declined. So that means some angle of image is changed. That answer we expect from a person. But when we ask a computer, it is two different images. So this image is different, and this image is different. How this computation will help us to think as humans and tell that, so this is maybe different image, but the different image is having same information what the original image is having. So that's what we have to understand and bring a model. So we can bring a model by using the scale invariant feature transform. So what are the informations we have in this image? So see, we can have a line here, but here the same line, but it was angle changed. That means same line, angle changed. And see here also same lines, angle changed. The size of this one is this curve is big, and this curve is small. And here some information is there. And what are the other things? And okay, so what we can understand here, some edges, these are all lines, no lines, corners are there, but they are all scaled. That means here a small, a big one is there, a small one is there. That means it's nothing but a scaling problem. If you understand properly the scaling problem, then we can tell we can design a model which with a computer algorithm, right? So as we are using here features which are invariant, so scale invariant, may they are same features, but scale invariant means what means, even the scaling if the two images are having same information but they are scaled, then our technique will consider that one as a scale invariant feature, scale invariant feature, right? So like that, this in transform is very popular. So let me give information about this one. Image content is transformed in local feature coordinators and that are invariant to translation, rotation, and scale and other imaging parameters. So see here, the translation, this translation is happen, this one is like this one like this, and rotation, so this one also like this, this was in this direction, this was in this direction. And scaling, so this one a big one and this is small one, here the line is big one and it is small one, right? So all these are compared here, see, all these are compared here. In this one, it is a feature vector where we can consider they are scale invariant, right? About scale invariant and how to process the scale invariant. So let us see. So scale invariant feature transform can be done by 4 steps. First one, we have to go for scale space extrema detection. Scale space extrema detection. Next one is a key point localization, orientation assessment, key point descriptor, and matching. So these are the things we are going to use in scale invariant feature transform. So let us see step by step. Scale space extrema detection. So what is meant by scale space extrema detection? So if two images are there, I want to see or create a scale space filter where the scales of that images should be understood, right? To detect the key point with the different scale, different scale, different scale space filters is used. Okay. Different scale space filters are used. That is called Laplacian of Gaussian, LOG. We call that one as LOG. Laplacian of Gaussian means we have a Gaussian filter here. Every time the image is scaled at a different octaves. This is first octave and this is second octave. Get the difference of these two things. We get the difference of these two things, and we will store this information. So this is called Laplacian of Gaussian. Laplacian of Gaussian. Okay, so like that we can store different scale information. In the first octave, I have this type of these things, and in second octave, I have different scales here. Coming to the next one, LG acts as a bold detector, detects bolts in various size. We can have maybe the shape or a size different, but as we're doing this LOG, left Gaussian, we can get the information of different sizes in the image. Gaussian kernel will with low gives high values of all corners, while Gaussian kernel fits well for the corners. See here, Gaussian kernel with low. So if you take this one as a low, will go high for small corners. So for a low Gaussian kernel, high values of corner information will be there. For a big one, I have a larger corner. I can capture the information small corner from here, and I have captured the information of larger corners here. But in earlier case, for Harry, detect only one window used. But here, the problem is solved by using this Laplacian of Gaussian at different scales. Right. So here I have a small, larger corners, and I have smaller corners. Like that, altogether, I can get the information about all the corners. And so we can find the local maxima area, across the scale, and which gives a list of values, which means the potential key. So from this, we can have a potential information, or we can have a very good feature key point. We call that one as a key at different scales. Like that, we have key points based upon keys. So this is what scale space extrema detection. So here the problem is rectified by this Laplacian of Gaussian. By using Laplacian of Gaussian kernel, we can have information of low corners and high corners also. So coming to the key point localization, so where local maxima occurred and where this local minima occurred, that will be done by localization. So once if I identify certain feature where that feature is localized, for that they use Taylor series expansion on scale space to get more accurate location of extrema. So what is the maximum point? By using this Taylor series, we can get a localization, and if the intensity at this extrema is less than a threshold, it is rejected. Right. So all the are not important. So we have to select a particular key points which are useful for our scale invariant future transform. Okay, so sometimes which some unwanted features also coming in our process. Those points can be eliminated by using these threshold values, where the intensities at this extrema is will be eliminated. For this process, we use difference of Gaussian. Difference of Gaussian have higher responses for edges. So edges also need to be removed. Sometimes unnecessary edges will be there. So there can be removed by using of this Gaussian difference of Gaussian. They can be used. We can use here Hessian tricks to compute the principal curvature. So what are the important curvatures that can be used, and other things are eliminated. So it is eliminated any low contrast key points and edge key points, and what remains is strong key points. This key point localization will help you to remove unwanted features points which are not necessary, right? So another one is orientation. Here we can see the inclination, what type of orientation they have, and what type of inclination we have. A neighbor is taken along the key point location depending on the scale, and the gradient magnitude direction is calculated in the region. Once the key point is identified, depending upon the scale, we will measure the orientation. So we have in image segmentation a gradient magnitude finding. Gradient magnitude means gx gy, or difference in x direction and difference in y direction. Based upon this gradient operator, we get the magnitude, we get the mod. So mod means mod gx plus mod gy, where gx is gradient in x direction and gy means gradient in direction. So by taking this gradient operation, we can identify in which direction the magnitude is there, or in which direction the key point is inclined. Based upon then we can identify the direction of the particular key point in a particular region. It is weighted by yeah, here also one point we have to notice: when we are doing this process, we come across some unnecessary key points, so those should be eliminated by using certain thresholds or based upon the prior information. The highest peaks in the histogram is taken, and above 80% it will be considered to calculate the orientation, right? So all the peak values are considered, but major orientations can be considered only above 80%. So this is also one of the important information. It creates key point with same location and scale but different directions. So it contributes to stability of matching. When we are doing matching, we have to identify the scaling information or feature, maybe in different location but in different scaling, but it should be matched with the same thing, right? So this is what we can do with the orientation assessment, right? Assignment, right? So one is a key point descriptor. Descriptor is a word we call describing. So once in the scaling feature, scale invent feature transform, not only finding the feature information or key, we will describe that information. So describing that information will help you to give better information, right? So now key point descriptor is created. So a 16 by 16 neighborhood around the key points is taken, and that one is made into 4 by 4 blocks, and in each block we have 8 bins. Bins means information, a group of information is considered. So bin orientation histogram is created. So see here, total 128 bins available, and they are represented with this 4 by 4 descriptor. So the descriptor, we can see here, the orientation will be clearly explained. So this total information is equipped in this one, right? So this total information is given by this descriptor, right? So in addition to this, several measures are taken: HU robustness against illumination changes, rotation changes also. And one more thing, scale invariant feature transform. Sometimes upon the descriptors based, we can get the illumination information also. Illumination information means when the light changes on the object, so the image may changes its properties. But when we have a clear descriptors information, we can identify that illumination changes also, right? So here that will be very useful. And key point matching. Finally, we have to match those points. That is very important. So once the features are extracted, those extracted features should be matched. So key point matching between two images are matched by identifying their neighborhood, nearest neighbor, right? So key point they are matched with nearest neighbor. But in some cases, the second closest match may be very nearer to the first. It may happen due to noise or some other reasons. So even in general cases also, when sometimes in recognizing the objects, we may do a fault. For example, a big size lemon, if you take when we compare with an Mozambique, then both are in same shape, but slight texture changes will be there. When we see both, they have the same features. In those type of cases, as we humans, we do some mistake depending upon the color, shape, and these things. In some cases, so the nearest one, second one will be giving the closest one. So in these cases, it will be treated as noise. For this type of justification and justification, we are going for further analysis, which I am not including here. Just we can see in feature matching is very important. So in matching, sometimes may noise will appear and it will tell wrong information. Right. So for that, in that cases, ratio of closest distance to second closest distance is taken. If greater than 0.8, that will be rejected. Yes, we have to do this type of some post processing things after getting the features extracted. Finally, the eliminated around 90% of the false matching, while discarded only 5 correct. So in this process, maybe the major noise contents of 90% false matching will be go. In this process, maybe 5% will be missing of correct, but we in zone, they, by doing this type of post processing things, we can get better feature information. Right. So let me explain the application. Almost the time is 8. So let me discuss about this application of shift invariant feature transform in panoramic stitching of image for images and close. Yes. So shift invariant feature transform is used in so many applications, but for this presentation, I consider image stitching. So we know that stitching is making two things one by using some process. Panoramic image stitching is one of the best application even we use in our mobile phones. An option is there by panoramic imaging. So if I want to take an image or if I want to take a photo of a huge object, it will be very difficult from a near distance. But if you go for a far distance, may you will lose the information. So in this process or in these cases, what we do is we take the images from near, and different images we will take. If we will take and by applying this computer vision techniques, we can process those images and we a big image. Example, if you want to take a group photo, if you take that group, a more number of people are there, we have to take our camera far distance. If you take your camera far distance, the quality of the faces in the image are reduced, so it will be not looking good. So what we will do, we take the image of total people, but in different, first we will take from left hand side and middle and like that we will do, and we will stitch those images. As we take the images very near, the information in the image like faces are very clarity. Finally we do, and we get the as a original image. That is what the background idea about panoramic images. In this image, I have taken uh, two images, but representing same information. But see here that one side we have this one, and the mountains are like this, and the same information we have here, but this is not there. This in this information, in this image, this information is not there, but in the image 2 this information is not there. But I want to get the both informations as an in a image. How to do this one? How to do this one? So here this scale invariant feature transform will help. First I will do is I will take this image and I will find the feature info, scale invariant feature, apply on that one, and I will get the feature vector. See, here also I will take the information. I will take this image and I will find the features in image, and these are the key points. See, the key point. If you identify these key points, all like corners, edges, all those informations are given. All this information are given, but these almost two images have common information. So by using a ransack, so this is one in linear liner. That means common features if you want to check. So this is one technique, but in discussing because of time, uh, this technique will be there. We are using only common inline uh, features in this two by using Ransac's inliner process. Finally, try these matching. These two are matching. So, and some other cases and some other processes are there like homography and changing the inclination, alignment, affine transform. But for simplicity, I'm giving just alignment of the features. Simply alignment. Okay, so here this feature and this feature, these features and these features are there. Sim by taking image and on the this image on this one. Final see the output. We get the total information, and some things are to be there to discuss. Some things are to be there to discuss here. Image blending. So one process not included here, that is called image blending. So we can see this to a patch here, but when we do the post processing we can remove this type of shade, and we can blend. We call that one as image blending. Finally, this is the image processing up computer vision using scale invariant feature transform. This is one application where we have panoramic image stitching, right? So this is what I have today to discuss, and tomorrow I may be discussing about topics. What second session coming computer how deep learning be uh, used, and how this computer vision transform how computer vision algorithms can be made simple by using deep learning. What is the difference between computer vision and deep learning techniques? These things we can discuss tomorrow. uh, I thank you very much for uh, today's session. Is there any doubts? Hello? Hello? Yeah. Hello? Okay, okay, sir. Hello. I want. I want. You want to share me PPT, sir? Yeah. Hello, sir. Your voice is not clear. Yeah, yeah, yeah. Please tell me, sir. Yeah, 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 yeah. I can share my PPT, sir. Sir, your voice is clear. Hello. Yes, yes. So I can combine and give this tomorrow. Slides also. Yeah, sir. Okay, okay. Sir. Yeah, yeah. Hello. Your your voice is not. Hello. Yeah, yeah, yeah. We will close the session, sir. Thank you for. Hello. Yeah, yeah, yeah. I can listen your voice, sir. Yeah. Thank you for giving me this opportunity for today's session. So tomorrow also the same process. Sir, can you share the link today, sir? Today's this video recording. So this recording. Please share me too. Okay, okay. Yeah, yeah, I will call you, sir. Your voice is not clear. Okay. Thank you. Thank you very much, sir. Thank you. Thank you, sir. Thank you.